Good, good. All right, we'll do this again. The two pyruvates will oxidize into acetyl-CoA. What that means is the pyruvate will lose a carbon and become acetyl-CoA, 2-carbon molecule. Now, when you do this, you're also making 2 more trucks. Now pay attention here, please. These 2 trucks are not the same as these 2. By this stage, you actually have 4 NADHs. 2 from here and 2 from here. Notice that when you have oxygen, you are not unloading these trucks. You only unload these trucks when you're fermenting. When you have oxygen, these 2 trucks are actually going to go deliver the electrons. So you now have a total of 4 NADHs. 2 in glycolysis, 2 in pyruvate oxidation. And in pyruvate oxidation is when the first time you lose carbon. Okay, now you have 2 carbons here and 2 carbons here. Each acetyl-CoA will initiate the Krebs cycle, its own Krebs cycle. Here it is. So this acetyl-CoA will initiate a citric acid cycle, or also called the Krebs cycle. This acetyl-CoA will also initiate another Krebs cycle or citric acid cycle. So for each acetyl-CoA, you take 1 turn of the cycle. Again, a long time ago, I used to be nice to my students, and I was just drawing a big circle, calling it the citric acid cycle, and trying to be nice to them, trying to keep it simple. And then you come to my exam and you say, what's this circle? Did you catch what I just said? On the exam, they're asking me, what is this circle? I'm like, I can't help you with that. It's the exam. Sorry. So I'm going to be nice to you and teach you the whole thing. Know that I'm not going to require you to learn the enzymes, thank God. I'm not going to require you to learn the molecular structures, thank God. But I'm going to have you dive in a little deeper so that you don't come on the exam and ask me, what is this circle? Because I get this impression that, oh, you're in trouble. Because if you ask me that question on the exam, then you probably don't know any of it. So I'm like, I feel real bad at that time because I can't answer that question anyway, so on the exam. I can answer it now. This circle is the citric acid cycle. It is also called the Krebs cycle. It initiates when oxaloacetate, catch it, combines with acetyl-CoA. I did not say oxaloacetate becomes, I said the 4-carbon molecule oxaloacetate combines with the 2-carbon acetyl-CoA to become citrate. It's 4 plus 2. Oxaloacetate combines with acetyl-CoA to make citrate. Because a lot of students by mistake think that acetyl-CoA becomes oxaloacetate. No, it doesn't. And oxaloacetate does not become acetyl-CoA either. I said combines with, and I'm stressing that word because so many students get this one wrong. And you can't look at it. If this one was becoming this one, then the arrow would be pointing towards the oxaloacetate. No, it's saying that the oxaloacetate is combining with acetyl-CoA to make citrate. That's what it means. 4 plus 2 equals 6. And I start with citrate and we'll go through the cycle here. Watch it. Citrate will isomerate. And notice what happens on the top one will also happen on the bottom one. Citrate will isomerize and become isocitrate. Isocitrate will lose a carbon and will become alpha-ketoglutarate. How do I know it lost a carbon? Follow the carbons. Look at that, 6 to 5. And watch this. Every time I lose a carbon, I make a truck. Every time I lose a carbon, I make a truck. Every time I lose a carbon, I make a truck. Now, you must say it the way I just said it. Every time I lose a carbon, I make a truck. You cannot say it the other way. You can't say, every time I make a truck, I lose a carbon. That is not true, because I made a truck here. Did I lose any carbon? No. And there'll be another one here where I'll make NADH without CO2 loss. You have to say it exactly the same way I'm saying it. And I'm saying this, every time I lose a carbon, I make a truck. That's the only way you're going to say it. Watch this again. Alpha ketoglutarate will lose a carbon, which means it will make a truck and become succinyl-CoA. See? Lost a carbon, made a truck. Succinyl-CoA will become succinate, and it will make ATP. Succinate will become fumarate, and you'll make the other truck at this step, FADH2. Fumarate will become malate, and then malate back to oxaloacetate. Look at that, you're making a truck without CO2 loss. So look, oxaloacetate starts, the reaction it ends with it, see? Because it's a cycle. You start with oxaloacetate, and you end up with oxaloacetate because it's a cycle. If you didn't do that, then it wouldn't be a cycle, and the whole thing breaks apart because you'll run out of oxaloacetate. So I know what you're thinking about sitting here today. How? What do I remember all of this? Very good question, because I had the same question a long time ago when I was a student like you. When my professor threw this up on the screen, I had to figure out ways. You have to look at it and come up with ways. So I will share what I did, and hopefully it works for you. And one of my students actually told me this phrase: can I add alpha, get it? Can I add some syrup for my oatmeal? That's a mnemonic to remember this, starting with citrate. I'll say it again. Can I add some syrup for my oatmeal? My daughter doesn't like oatmeal, so she changed that one to omelet. And she changed one to salt. So she says, can I add some salt for my omelet? That's fine too. I don't care. Oatmeal, omelet, I don't care. So that's the mnemonic you're going to use to remember the order of things. Here's another one. 665 5/4s. 665 5/4s to follow the carbons. And then I remember this. Every time the number drops, I'm losing a carbon, which means I'm making a truck. Watch this. Citrate, 6 carbons. Isocitrate, 6 carbons. Did I lose carbon? No. From 6 to 5, that's alpha ketoglutarate. From isocitrate to alpha ketoglutarate, I lost a carbon. I made a truck. From alpha ketoglutarate to succinyl-CoA, I lost another carbon. I make another truck. Here's that weird one. Between the two sounding words, I make ATP by SLP. Again, call me weird, call me whatever. I remember it. From like God knows when. This is what I came up with when I was a student. Most likely before you were born. But I still remember it. And of course I remember it because I teach it every semester too. Called multiple exposure. So between the two sounding words, succinyl, succinate, I'm making ATP by SLP. Here's another one. When I make fumarate, that's when I make that FADH2. See it? Fumarate, FADH2. FADH2. From fumarate to malate, I remember, boring, there's nothing going on. From malate to oxaloacetate, all of a sudden I remember my alphabetical order. MNO, MNO, MNO. It works. If you like this approach, go ahead, use it free of charge. If you want to do something else, that's fine. But whatever it is that you need to do it by Thursday, because you have a quiz on this on Thursday. That's why I sent the eukaryotic YouTube videos to get you started with it. So each cycle of the Krebs cycle, also called the citric acid cycle, makes 3 NADHs, 2 carbon dioxides, 1 ATP, and the other truck, FADH2. But we don't do 1 cycle. We do how many? 2 cycles. So now, from 1 glucose, you're going to end up with 2 NADHs from here, 2 ATPs from here. 2 NADHs from pyruvate oxidation, 2 CO2s. 6 NADHs from the Krebs cycle. 2 ATPs from the Krebs cycle, because you do it twice. 4 CO2s and 2 FADH2s. You always have to do the tally. At the end of each stage, can you do the tally and do your numbers work out right? Because if they don't, then you're missing something. So this is what we have. Now the CO2, because it's small and non-charged, will leave the cell by what process? Small and non-charged, it will leave the cell by what type of diffusion? Simple diffusion. Yeah. So now, at this stage, we have a total of 10 NADHs and 2 FADH2s. If you count all the delivery trucks, you have 2 NADHs here, plus 2 more, that's 4, plus 6 from this one, that's 10. And you have 2 FADHs from this one. Those are your delivery trucks. All right, what are they delivering? Electrons and hydrogen. Who are they delivering to? The electron transport chain. Now, this is where the fun begins. Here's the electron transport chain. In bacteria, it's in the cell membrane. In your cells, it's in the inner membrane of the mitochondria. That's where the difference is. So in bacteria and in your cells, you have 1, 2, 3, 4 complexes. You also have ubiquinone. Bacteria has that too. Cytochrome C, bacteria has that too. So it's no different than ours. The only difference is location. Cell membrane versus inner membrane of your mitochondria. All right, the delivery trucks will do what the delivery trucks do. They deliver. NADH delivers all the time to complex 1. FADH2 doesn't know complex 1. It goes to complex 2. Get it? FADH2 goes to complex 2. Again, another thing to remember. When NADH delivers the electron, it becomes oxidized. So this is like your truck reaching your new home, unloads the furniture. That means the truck is leaving your new home empty. Unload the furniture, it leaves empty. This is the reduced form. This is the oxidized form. So the NADH delivers the electron to complex 1 and it will leave empty. It goes and reloads in glycolysis, pyruvate oxidation, citric acid cycle. So watch it happen here. Watch this. NADH delivers the electrons to complex 1. Once complex 1 gets the electrons, it opens up a channel and pumps protons, hydrogen ions, into the space right here. Okay, then what happens? What happens is complex 1 wants to give the electrons to complex 3. Complex 1 does not give the electrons to 2. Complex 1 wants to give the electrons to 3. But there's a problem. The problem is this. Complex 1 is standing in the membrane, it doesn't want to move. Complex 3 is standing in the membrane, it doesn't want to move. And they're too far away from each other. So it relies on a relay system that actually moves, and it's this guy, ubiquinone. These guys do not move. They're standing still in the membrane, but ubiquinone can move. So ubiquinone is going to go to complex 1, pick up the electrons, and go to complex 3 and deliver them. And watch it happen here, please. So the electrons go to ubiquinone. Ubiquinone delivers the electrons to 3. 3 opens up the channel and pumps protons. Same thing. 3 and 4, they don't move. So they rely on cytochrome C to deliver the electrons between them. So cytochrome C is going to pick up the electrons, give it to 4. 4 will release more hydrogen into that space. All right, we'll deal with the hydrogens a little later, but let's keep working with the electrons. Notice the electrons, they're coming from NADH, complex 1, ubiquinone, complex 3, cytochrome C, complex 4. Oh, someone has to take them. I can't keep them here. See, complex 4 must get rid of the electrons because it only has 2 hands, for example. If complex 3 wants complex 4 to take more electrons, it can't until it gets rid of the previous 2. And that's where oxygen comes in. And that's why you breathe. Your breathing and bacteria, aerobic, obligate aerobes also need oxygen for this purpose. Oxygen is the final electron acceptor. It will take the electrons from complex 4 combined with hydrogen in the soup of things and it will become water. So look, the oxygen that you're breathing right now, within the next couple of seconds or so, will become water. But you have to take that because you must get rid of the electrons from complex 4 so that complex 4 can participate in the next event. If the next event occurs with complex 4 having the electrons still, it'll be equivalent to this. Let's say I'm complex 4 and you give me electrons. I have to hand it off to oxygen so that my hands are free to take 2 more in the next event. Let's say you don't do that. Let's say I get electrons, but I can't give it to oxygen. Then you try to give me 2 more, and I'm like, I can't. I can't. I have to get rid of them before I take 2 more. Then complex 3 will do the same thing. Oh, I can't give them to 4, so I can't take electrons from complex 1, and so forth. The whole thing backs up. You know when that happens? In eukaryotic cells, the poison that blocks this step right here is cyanide. Cyanide blocks this step right here. Cyanide is definitely a poison, and it's a simple, complex 4 wants to transfer the electrons, there's an enzyme for that. It inhibits this enzyme. The whole thing backs up, and the cell dies instantly. You know how fast cyanide kills. Kills really fast. Because everything about you screams, I need ATP. And you just turned it off. With cyanide, you turned everything off. Why? Because you blocked this event and the whole thing backs up and it shuts down instantly. It's amazing how fast it works. So now we know the importance of transferring the electron to oxygen and the importance of oxygen being the final electron acceptor to keep this process going. All right, let's look at the other trust. FADH2, let's look at that one. FADH2 goes to complex 2. So that's one difference you need to know. FADH2 does not go to complex 1, it goes to complex 2. Here's another difference that you need to know. Complex 2 does not pump hydrogen. It's just a relay system. The rest of it is the same, thank God. I don't have to remember anything new. Look at that. It's the same. So if you put this information together, you realize something. That when we're dealing with NADH, 3 complexes are pumping hydrogen. With NADH, complex 1, complex 3, complex 4 are pumping hydrogen. When we're dealing with FADH2, which 2 complexes are pumping hydrogen? 3 and 4. So all that hydrogen in that space is trying to create something called the electrochemical gradient. It is a gradient. It's a gradient because it's a difference in the concentration across a membrane. But this is a charged element. So it's called an electrochemical chemical gradient. Let me write it on the board so you know what that. Very important thing to know. Now, I tell students, think of that as the battery, as a battery. This is a charged battery. So what we're doing here, when we put hydrogen in that space, we're creating a charge distribution across the membrane. That's no different than a battery. So you're charging a battery. This is equivalent to you charging your phone for 12 hours, and this one for 2 hours. Which one will you get more text messages out of? NADH or FADH2? And obvious, right? So, because 3 complexes are involved, you're going to create a greater, more charged electrochemical gradient. FADH2 will create an electrochemical gradient, but it will be just a slightly weaker one. So there's a conversion factor. 1 NADH will make 3 ATPs at the end of this. 1 FADH2 will make 2 ATPs. Because it's a weaker battery. It's like saying, I'll get 3 text messages with this one, but only 2 with that one, for example. So now we know the conversion factors. Now, let's look at them both working together, because we know they both work together at the same time. But thank God I didn't teach it that way, because it would be overwhelmed. Here's both of them working together. That's what it would look like. The NADHs are delivering the electrons to complex 1, ubiquitin 3, cytochrome C4, back to oxygen, becoming water. At the same time, FADH2 is delivering the electrons to complex 2, ubiquitin 3, cytochrome C4, the oxygen becoming water. The electrochemical gradient is building up in this space here. That's the battery. Why is all of this happening? It's because of this guy. ATP synthase. Now, a lot of students blame this complexity of cellular respiration on the professor. Don't blame it on me or any other professor. Blame it on this one. The reason is, I tell you something, ATP synthase is the enzyme that's actually gonna make the ATP. I mean, look at the name. It's called ATP synthase, an enzyme that makes ATP. The problem is, it's sleeping on the job. It's in there, in that membrane, sleeping. Someone has to wake him up to make ATP. Wake up! Oh, I know a good way to wake him up. Fire hydrogen right through him. That'll wake him up. That's what's happening right here. Take the hydrogen and fire it right through ATP synthase. That'll wake it up. And that's what actually happens. ATP synthase will feel that hydrogen going through, and it will do this. It will wake up, and it will pick up an ADP, a phosphate, and it will make ATP. That's this one. We call that chemiosmosis. Chemiosmosis. So what I'm trying to tell you is this. 1 NADH, watch this one. Watch, be careful please. 1 NADH will pump enough hydrogen. They will go through ATP synthase to wake up ATP synthase to do this. 1, 2, 3, and they'll go back to sleep. That's why it's a conversion factor of 3. 1 FADH2 will pump enough hydrogen in that space so that when they come back through ATP synthase will wake up and make how many? And it will go back to sleep. But we don't have 1 NADH. How many NADHs do we actually have? 10. So all 10 of them are delivering the electron. That means they're going to dump a whole bunch of hydrogen ions there. Enough to do this to the ATP synthase. Wake up and do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to what? All the way to
30.
What? 30. Because it's a conversion factor. 1 NADH makes 3 ATPs, That means 10 NADHs will make 30 ATPs. Good. Let's do the same thing for FADH2. One FADH2 makes 2 ATPs. That means 2 FADH2 will make 4. The 2 FADH2s will activate this enzyme to make 4 ATPs for a total of 34 ATPs. But remember, you have 4 other ones. You have 2 ATPs that you made by glycolysis, and that's by SLP. Remember those 2? And 2 ATPs that you made during the citric acid cycle, also by SLP. For a grand total of 38 ATPs. Okay, if these are by SLP, what are these made by? Well, they're made by this process, but it's called oxidative phosphorylation. This is called oxidative phosphorylation. The combination of the electron transport chain and chemiosmosis. So electron transport chain plus chemiosmosis, which happens in the cell membrane of bacteria, is collectively called oxidative phosphorylation. And that's where you get most of the ATPs. So I always teach based on maximum outcome here. The maximum yield per glucose is 38 ATPs. The actual yield can vary, and then we're not going to go through all of that. See, the maximum yield assumes something. It assumes that all the hydrogen ions went through ATP synthase. With a direct correlation there. All the hydrogen ions went through ATP synthase and made 38 ATPs. But in reality, that's not what happens. Most of them go through ATP synthase, but let's say this one, for example, says, no, I don't want to go that way. I want to do something else. Then you'll lose that one. So you may not get exactly 38. You may get like 36. But don't worry about that detail. I always teach based on the maximum yield. Maximum yield is 38 ATP. Actual yield can vary. So this is aerobic cellular respiration. This is what an obligate aerobe would do. This is what a microaerophile would do. This is what a facultative anaerobe would do in the presence of oxygen. Now the question is, what about anaerobic respiration? Oh, you're gonna scream, oh my God, I have to know this one too? Well, look at it carefully. What do you see? It's the same one, thank God. So again, when my professor threw this up there, I went, oh no, there's another one. Then you look at it in detail, what? It's the same one. The glucose carbon take 2 ATPs, spark it, make G3P, energy investment phase, energy payoff phase. I got the pyruvates, I have oxygen, I'm gonna oxidize the pyruvates. I got 2 over here. It becomes acetyl-CoA, I make 2 turns, everything is the 5. I still have the 10 and the 2, everything. So where is it different? At the end. That's where it's different. Look at that. It's anaerobic cellular respiration, means it does not use oxygen. It uses something other than oxygen. Some bacteria, instead of oxygen, they use nitrate. Instead of oxygen, they use sulfate or carbonate. That's the difference here. That's it. It's at the end. Some bacteria will use the nitrate, and make it nitrite and go all the way to gas, nitrogen gas. Which ones would those be? The nitrifiers, yeah? The ones that take the electron, give it to nitrate to become nitrite, and then it goes all the way to nitrogen gas. Those are your denitrifiers, like Pseudomonas, for example. So look, anaerobic respiration, exactly the same as aerobic respiration, thank God, except the only thing is at the end. Instead of oxygen, I have choices. By the way, we only talk about 3 possible choices, but there are more, but we don't talk about the other alternative choices. The end. Thank you.